Today we're going to be talking about operational amplifiers. The operational amplifier, or op-amp, is an active device, meaning it requires external power, used to perform simple mathematical operations on an input signal or combination of input signals. Modern op-amps are one of the most utilized integrated circuit devices in modern electronics. An integrated circuit device is one which contains internally all of the transistors, resistors, and capacitors necessary to perform the signal operations. Now, the internal workings of an op-amp, which contain upwards of 10 transistors, resistors, a few capacitors, and things like that, is actually well beyond the scope of this class. Instead, we are going to be looking at an op-amp from a component level view. So the first thing that I'd like to do is to identify the circuit schematic representation of an op-amp. Now, all amplifiers are represented traditionally by triangular. So this triangle is the universal symbol for an amplifier in block diagrams and things like that. An op-amp is a specialized amplifier. And it's specialized because it's what's known as a differential amplifier. It multiplies the difference in some signals. So for the operational amplifier, we have two inputs. We have an inverting input pin here on the left-hand side and a non-inverting input pin as well here on the left-hand side. The inverting input pin is denoted by the minus sign, and the non-inverting input pin is denoted by the plus sign. We also have an output pin over here on the right-hand side. So this is our first example of a three-terminal device, except that it's actually much more than that. Because our op-amp is an active device, there's going to be at least two more pins. VCC plus, which is where we would connect a positive power supply voltage, and VCC minus, which is where we would connect a negative power supply voltage. Now, for the scope of this class, we are going to assume that all of our op-amps are biased with the correct power supply voltages to make it work the way we expect it to. So after this point, you won't see the power supply voltages drawn into the circuit, but they are there, assumed to be there, powering the op-amp so that we can perform our circuit analysis. Now, in circuits 1, we are going to confine our analysis to ideal op-amps. And the behavior of an ideal op-amp is governed by two very straightforward rules. The first rule is that no current may flow into or out of the input terminals. So in our op-amp schematic drawing up here, that would mean that this current, which we could call I plus, flowing into the non-inverting input terminal must be equal to 0 amps. And similarly, this current I minus flowing into the inverting input terminal must also be 0 amps. That's how we are applying op-amp rule number 1. Op-amp rule number 2 states that there is no voltage difference between the input terminals. So applied to our schematic diagram, that would mean that the potential difference between these two input terminals must be 0 volts. Now, a happy side effect of op-amp rule number 2 is that if there's no potential difference between these guys, then if we call the voltage present with respect to ground at the non-inverting input terminal V plus, and the voltage present with respect to ground at the inverting input terminal V minus, the fact that there is no voltage difference between the input terminals means that V plus must be exactly equal to V minus. And this is going to come up an awful lot in our analysis of operational amplifier circuits. Now, one thing that I do want to point out is that these ideal op-amp rules are only applicable for what's called a negative feedback op-amp circuit. So let me explain what feedback means in an op-amp circuit very briefly. So here is our basic op-amp, non-inverting input pin, inverting input pin, and we can draw the triangle with the inverting on top or non-inverting on top as we choose. If we have a connection between one of the input pins and the output pins, this is called feedback. It may be accomplished by a wire, or it could be accomplished by a resistor or some other electrical component. This is a particular example of positive feedback because it's a connection between the non-inverting input terminal and the output terminal. Okay, so positive feedback is between the non-inverting input terminal and the output terminal. A practical example of positive feedback would be the feedback that you hear when somebody talks into a microphone that's too close to a speaker cabinet. So the person's voice is the input and the output is the signal generated from the speaker cabinet. So you speak, it generates a pressure wave, which is picked up by the microphone and then amplified by the speaker cabinet. Well, the speaker cabinet also produces a pressure wave, which can be heard by the microphone. And so you get a cyclical increase in the output signal that results in that high-pitched squeal that most of us are not very fond of hearing, okay? So that would be a representative of an unstable system, which is what most positive feedback systems are. In this class, we're going to be working with negative feedback systems predominantly. And so in a negative feedback system, we simply have our feedback loop between the inverting input terminal and the non-inverting, or in the output. Like so. So this is negative feedback. And again, this occurs when we have a signal path connected between the inverting input terminal and the output terminal. And you'll see that all of the examples that we're going to work here in circuits 1 are examples of negative feedback. So let's take a look at our first example. So this is a fairly simple and straightforward op-amp circuit. I'm going to write our rules again over here. Op-amp rule number 1. Current flows into or out of the inputs. Op-amp rule number 2 is no voltage drop across the inputs. So applying op-amp rule number 1, and our ultimate goal in this problem is to determine what the value of our output voltage is. Okay. So applying op-amp rule number 1, we could observe that this current, which I'm going to call I minus, is equal to 0 amps. And I could also say that this current, which I'll call I plus, is also equal to 0 amps. Applying op-amp rule number 2 says that there's no voltage drop across our input terminals. So we could interpret that as this voltage V plus with respect to ground is obviously 6 volts. And so this voltage V minus with respect to ground must also be 6 volts. So let's see how these two ideal op-amp rules help us determine the output voltage of our circuit. Well, if we look at what's going on with op-amp rule number 1, if no current can flow into or out of the inputs, that means that the current flowing through the 2 kilo ohm resistor must be 0, which implies that the voltage drop over the 2 kilo ohm resistor is 0 volts. Our second op-amp rule allows us to write a Kirchhoff's voltage law equation starting from ground here on the left-hand side and going to ground here on the right-hand side. So we started and ended at the same potential. And so what we have is -6 volts minus 0 volts, the drop between our input terminals, plus 4.5 volts, the drop over our topmost source, plus 0 volts, the drop over our 2 kilo ohm resistor, plus V out is equal to 0. And we can rearrange this guy and we would find that V out is equal to 6 volts minus 4.5 volts is simply 1.5 volts. So we've successfully analyzed our first op-amp problem predominantly by applying the two ideal op-amp rules and then using elementary circuit analysis techniques like Ohm's law and Kirchhoff's voltage law in this case. Now let's increase the level of difficulty a little bit here. So we're going to start by applying our ideal op-amp rules again. Oops, kind of ran away from me. So we know that this current is 0 amps, and we also know that this current is 0 amps. So that's ideal op-amp rule 1 applied. Now op-amp rule 2. We have 0 volts, so we know that this voltage V plus is going to be exactly equal to this voltage V minus. So ideal op-amp rule 1 tells us that the current that's being supplied by this 2 milliamp source leaves the source and all of it must flow down through that 4 kilo ohm resistor because none of it can branch off and flow into the input terminal. So we can use that to determine that our voltage present at our non-inverting input terminal must be 2 milliamps multiplied by 4 kilo ohms is 8 volts. Application of ideal op-amp rule number 2 tells us that V minus, the voltage present at our inverting input terminal, has to be the same as the voltage present at our non-inverting input terminal. So it must be 8 volts as well. So what that means is that at this node, there is an 8 volt potential with respect to ground. So we could say that there's going to be some amount of current flowing through that 2 kilo ohm resistor because there's an 8 volt drop over it. And let's call this current I. That same amount of current I must be flowing through the 5 kilo ohm resistor. because we know that none of it can branch off and flow into the inverting input terminal. So we can write our current I is 8 volts divided by 2 kiloohms is equal to 4 milliamps. And we can also say that our current I is our output voltage, V out, minus the voltage present at the inverting input terminal, which is 8 volts, divided by 5 kiloohms. And if we rearrange this second expression, what we'll find is that I, which is 4 milliamps, times 5 kiloohms plus 8 volts is exactly equal to V out. And thus, V out is equal to, let's see, 20 plus 8 is 28 volts. So we've analyzed another circuit. This time we had to get a little bit more into the use of our Kirchhoff's current law and things like that. We could have also written a KVL equation and figured things out, but I think KCL was the easier route here. Let's increase our level of difficulty a third time. So now we have a bit more of a complex ideal op-amp circuit, but we can really approach it in much the same way. Applying ideal op-amp rule number 1, this current must be 0 amps, and this current must be 0 amps. And applying op-amp rule number 2, potential difference between these guys must be 0 volts, which means this voltage here, V plus, is identical to this voltage here, V minus. So, using this, we can see that up here in the top left-hand corner, we really just have a single loop circuit where all of the current that's leaving the 7-volt source is going to flow in a loop like this. So we can treat that section of the circuit as, let's see, here's our 5 kiloohm resistor. Here's our 3 kiloohm resistor. Here is our 3-volt source. Let's tie both of these guys to ground. And what we're looking for is this voltage drop. There are a couple of different ways to determine it. Superposition would make it pretty easy, but instead, let's simply use really Ohm's law and then Kirchhoff's voltage law. So we know that there's going to be some current, let's call it I1, that's flowing around this network in a clockwise fashion. And so we would have -7 volts plus 5 kiloohms plus 3 kiloohms times our current I1 plus 3 volts is equal to 0. From this, I1 is equal to 7 volts minus 3 volts divided by 8 kiloohms is 4 volts divided by 8 kiloohms is 0.5 milliamps. If my mental math here is correct. We can use this and write another Kirchhoff's voltage law loop that says negative V plus 3 kilo ohms times I1 plus 3 volts is equal to 0. And if we substitute in our value of I1, that gives us V plus is equal to 3 kilo ohms times 0.5 milliamps plus 3 volts would be 3 times 0.5 plus 3 is 4.5 volts. So we have 4.5 volts here with respect to ground, which means we also have 4.5 volts here at our inverting input terminal with respect to ground. And now things are going to look very similar to our last example. So there is a current, let's call it I2, that's going to flow down through the 1 kilo ohm resistor because there is a voltage drop over the 1 kilo ohm resistor. And ideal op amp rule 1 tells us that this current, which is coming from our output voltage, is going to flow through the 3 kilo ohm resistor, and that these two currents are the exact same thing. So we could say then that I2 is equal to 4.5 volts divided by 1 kilo ohm is 4.5 milliamps. And we could also say that I2 is equal to V out minus 4.5 volts over 3 kilo ohms, which allows us to rewrite this as V out is equal to 3 kilo ohms times I2, which is 4.5 milliamps, plus 4.5 volts. So 3 times 4.5 is 13.5, plus another 4.5 is, I believe, V out is equal to 18 volts. So those are 3 example problems detailing how to use the ideal op amp rules, as well as Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law to determine the different voltages within the circuit, be it the voltage present at the non-inverting input, the voltage present at the inverting input, or the voltage present at the output of the op amp. Our next lecture will be detailing common operational amplifier topologies and applying these exact same rules to understand what's known as the gain relationship or input-output relationship of a select number of operational amplifier circuits. Thank you guys for watching.